let's talk about a general solution for vibrating systems. Right? So oftentimes in mathematics, we want to get the most generalized solution that we can. I think I can do it here. And so a generalized solution is one that just allows us to solve more and more problems. Also, it expands better when we start to add things like damping and forcing functions or nonlinearities. Once you get into nonlinearities, which we don't even do in this class, you really want a generalized equation, right? It's just helpful. So let's go ahead and build that. But however, we want to do a little bit of review to get to that. So in our generalized equation, right, there's lots of different solutions we can have for these our system. So we're going to end up with the same solution, right? So we're not solving for anything different. We're just kind of doing it in a more generalized way. So let's do a little bit of review here on complex numbers. Vibration analysis, right? We can use complex numbers to solve our equations of motion. And so what do you guys usually use for your imaginary number? Anyone else? How's your option? What? -1. Jude, you're an electrical engineer. What do you guys use for complex numbers? J's. Yeah, because I is a current, right? Yeah, I don't know why. I don't know why like mechanicals use I don't get it. So we're going to use J. So when you look at your springs and dampers, which look like resistors and capacitors, you're not drawing a circuit, right? Helps to make that clear. So complex numbers. We want to look at an imaginary number. J, right? So we can say sometimes. Let's just go not I in this class. And sorry to throw that at you. It's kind of the convention that's used more often in vibrations. I don't know, it's about 50-50, but it just makes more sense to me anyways. So let's go with J is equal to the square root of -1. Right, so we're not defining anything too fancy there. J squared is equal to -1. Stuff you've seen before, right? So a general complex number X can be expressed as X is equal to A plus B J. Right? So what is A here? What part of A? What part of complex number is A? Real, and then B is imaginary. I think I got to get one of those hand guards. And B is imaginary. And we can draw this out onto the complex plane, which is what we're actually interested in here. So it looks something like this. Okay, so we have our imaginary axis, which is equal to B. We have our real axis equal to A. And so we have a point here. Just kind of call that A is equal to lower A comma B. I really should call that X. No, I don't want to call that X. Okay, so our distance here, right, our magnitude is going to be the amplitude of X, which is equal to the amplitude of A, plus BJ, right, which is equal to I realize that's way too small, which is equal to the square root of A squared plus B squared. Right, so the other thing that we're going to be interested in here is our conjugate pair. And so where's the conjugate pair of AY? Do you remember that from? What class would you have that in here? FAQ. So where's the conjugate? Conjugate's a negative, right? That's how I always think of it. Is it a negative about the imaginary or a negative about the real? Two options. Imaginary? Who's on the imaginary team? Who's on the real team? So your conjugate.
There's always a thing like a complex conjugate.
Yeah. So it's a negative imaginary. So it's about the real. It flips over. Yeah, I see what you're saying. So we have A star is equal to A comma B, A comma negative B. That make sense? So, yeah, right now. So that's our negative B. And that's our conjugate pair.
Anything by the RE, like the real out of the frame, or did you just write under it? Real equals to the square root of A squared.
Oh yeah, that's all. Sorry. That's all one mess. That make sense? I just didn't have any room for the right. And so this is called a R-grand plot. And I don't know who R-grand is. I will look that up. We are missing a key part of your vibrations education. So talk about someone I do know, who is Euler, who is our Swiss mathematician who died in Russia. So I'm going to go back to making this bigger. So Euler's formula is EJ psi is equal to the cosine of psi plus J sine of psi. So this doesn't give me, I'm not a big fan of this eraser. Right, so pronounced Euler's like a can of Euler. If you pronounce it Euler's, I don't really care. That's what everyone always says, and that's what I said for the longest time, but technically pronounced Euler's. So we can have this Euler's equation, which allows us to relate a space in the complex plane to a real plane. And as J equal to the square root of -1, we can write this as E negative J psi is equal to the cosine of psi, minus, that's what we're changing here, minus J sine of psi. So that kind of gets us caught up on reviews. We'll draw the plot next time. All right, let me just draw it real quick. So we've got a plot. Ooh, I can do axes. So we have any point on our term, on our circle, is E J psi is equal to the cosine of psi plus J sine of psi. Right? So what's this? So if this is psi here, what's this bottom portion going to be? It is real. That's correct. But what's the length of it? Yeah. So the cosine of psi. Well, so this is a unit circle. It is J. You are absolutely correct. But we typically kind of just call it a unit circle. So we just say the cosine of psi. Does that make sense? But it's absolutely J cosine of psi. But it's just kind of implied. And then the sine of psi. And so again, the difference between these two equations, this was kind of asked, these look the same. They're not. This one has a negative sign. And a negative sign. That makes sense? So that's the difference. So you have E to the J psi equals cosine of psi plus J sine of psi, and E to the negative J psi is equal to cosine of psi minus J sine of psi. Right? All right. So let's go ahead and formulate the general solution. All right, so what is a general solution? I want to figure out, I gotta figure out what anyone know what a general solution is? Right, mathematically, general solution. Take a stab at it. The generalized solution. Right, so we're looking for something that is just going to express our system, in our general ODE formulation. Right, so this gets a little mathematically wizardy, right? So there's lots of substitutions, and we'll make a substitution and then show why we made the substitution, right? So if you're writing down your notes, which you should be, and you get to like, oh, where did that come from? I'll try to point out our substitutions or assumptions that we're making, and then we'll come back to them. Right, but if after a couple lines it doesn't make sense, feel free to raise your hand. But if right away it doesn't make sense, just let me get a line or two down. That makes sense? Okay, so let's solve the equation of motion in a more analytical method using a theory of differential equations. Right? So our equation of motion I'm real tempted to see. It's fine. Does this little cursor bug you when I write? Or does it just bug me? It's fine. I'll get it next time. Okay, so let's solve our equation of motion in a more analytical manner. So to do this, right? So to solve, assume that x of t can be expressed as our constant a times e lambda t, right? So we're going to assume that this is a solution to our equation.
What's that variable in front of the e again?
Lambda. Oh, in front of the e? A.
Okay.
Yeah, like A as an apple. All right, so A and T here are obviously our non-zero constants, right? We have a 0 at A or a 0 at T. This whole thing kind of falls apart. So because we're doing vibrations, we're going to want our velocity, x of t, x dot of t, right? And so what is the derivative of A e lambda t? T. So that's fine. I mean, I'd be, what? The lambda comes down. Yeah, don't worry. There's no way I could remember it either. Well, I can because I've done it so many times. But okay, so A lambda E lambda T, or let's put our lambda out in front. Lambda A lambda A E lambda T, and then X double dot is going to be pretty simple. Just going to pull down our lambda again, and we're going to have lambda squared AE lambda of T. Okay, pretty simple. So we have an equation of motion. What's our equation of motion? We don't have any damping, so it's just mx double dot plus kx equals 0. So let's go ahead and put our solutions here into our equation of motion, right? And just kind of see where that gets us. So that breaks down pretty simply to, so our equation of motion is m lambda squared AE lambda t plus k AE, whoop, sorry, lambda t. I wonder real quick if there's a way for me to we'll figure it out later. Okay. So this is our equation of motion. If you look at this equation, which equals to 0, what do you think we can pull out? Yeah. Well, yeah, AE lambda t, right? We have to leave the lambdas in there. So let's go ahead and pull those out. Divide by, divide by the left, right? Well, that's pretty easy. We'll just get rid of them completely then. So we end up with m lambda squared plus k is equal to 0. That seems pretty simple, right? That's a nice short equation. Everyone likes short equations. So this can be done because our AE lambda t is never actually going to equal 0, right? Therefore, the equation itself is never divided by 0. Makes sense? It just kind of doesn't matter too much. But the quadratic formula, so we can solve this using the quadratic formula, right? Gives us, you can play around with it if you want, but lambda is equal to plus or minus the square root of negative k over m, which is equal to the square root of k over mj. And j is our imaginary number, pulling it outside, getting rid of the negative. What's the square root of k over m? Sorry. Omega n. Omega n j. And the reason I'm stickler on that is we actually use omega without a subscript later in the class for a forcing function, right? So we have an omega n, an omega d, and an omega. We have 3 omegas in the class. So lambda is equal to, plus or minus omega nj. So here, good question. So here it's not a negative frequency because we have our imaginary component. But what it does tell us is we have 2 solutions, right? Which is very helpful. So this tells us we have 2 solutions. One solution positive, right? One solution negative. So we can go ahead and put this back into our assumed solution, right? And our assumed solution is x of t equals ae lambda t. And this becomes, so we have two solutions. So we have 2 solutions now. One, we have our positive solution, x of t is equal to a1 e omega n j t. I'm going to put a positive sign there just so we're explicitly clear, not needed. And then 2, x of t is equal to a1 e negative omega n j of t. That makes sense? Any questions about that so far? Okay, so those are our 2 solutions. And they're only valid for linear systems. All right, so from differential equations, what does a linear system give us for solutions? There's a special rule about solutions for linear systems, right? And remember, we're talking about 2 linear systems. Oh, I'm sorry, there's a mistake. That's A2. That look better? We're talking about 2 linear systems with scalars, right? So remember, you can always adjust your scalars. But if you have 2 linear systems, what can you do with them? You could. That's not what I want. Yeah, but we can also add them, right? Because, so you can think of that xt as a1e to the omega njt, but it's also a1e to the omega ngt plus a2e to the negative omega njt, right? And then all we have to do is adjust our scalar values. That makes sense? So for differential equations, the sum of the solution is a solution.
Professor, that's assuming linear system, right?
Yeah. So if you have a nonlinear system, right, you can't just easily adjust the scalar values out front. Does that make sense? Because they don't add up the entire way. If you have two lines at two different slopes, right, or if you have two lines at two different slopes, you can adjust the scalar to get whatever slope you want, right? But it's still going to be a linear system. Okay. So this is important, right? Sum of the solution to the solution. So that gives us x of t is equal to a1e positive omega n jt plus a2e negative omega n jt, right? So in this solution, a1 and a2 are complex valued constants of integration, but constants nonetheless. So I'm going to go ahead and circle that. So that's an actual solution to our problem, right? Is it a very useful solution? If you tried to solve x of t with this, is it a very useful one? Like, how are you going to code that? Got complex values? Probably not, right? Just by the fact that they're complex. However, it is a solution.